Hi, everyone. My name is Eric. I'm a security engineer at Google. I don't work on the Go team or anything, but I like Go, and I use Go for a lot of stuff, so I was hoping to give this talk. A quick order of business. This talk has a lot of code in it, and you are not going to be able to take notes and record all the code. So the slides I just tweeted them out. If you would like any of the code from this talk, please get the slides, because it's going to go fast. And with that, we're just going to dive right into it. So this is a talk about HTTPS. There are other types of PKI, like if you're a masochist and use PGP, you can. Good start. And I also just learned that email uses certificates and everything is awful, but this is a talk about HTTPS. And I think we all have this kind of intuition that HTTPS is up on the uptick. Really big websites like the New York Times have moved their stuff over to HTTPS, and Google actually publishes transparency reports around its platforms of how often they're browsing HTTPS. And so there's actually data to back up this sort of assumption. But I don't want to give this talk because of this, actually. I want to give it because of this other mentality around security engineering that's been coming very prominent lately. Every security startup with their salt has Beyond Corp or Zero Trust in their marketing materials somewhere. And this is sort of a mentality that security is no longer about building a very strong perimeter around your infrastructure, that you can't just have a VPN and say, outside is where all the bad people are, but inside here is trusted. And we're going to start moving to this point where everything, even inside of your VPN or inside of your little corporate network, is going to have to require authentication, encryption, authorization. And I think that for anyone here at GopherCon, whether or not you're a security engineer or not, whether or not you're building front-end services or you're building back-end databases, you're going to have to think about HTTPS. And in fact, you should probably only be operating over something like HTTPS. So we're just going to dive right into it and talk about how you set up HTTPS in Go. So the first thing we need to talk about is signatures. You all might be familiar with this. The way a signature works is that it's some mathy stuff, but basically, I go ahead and create a private key and a public key, and the private key is something that I hold on to, and I don't let anyone see. And the public key is public, so I can share it with all of you, and you can all have my public key. Now, you can do a lot of stuff with this, but one thing you can do is sign a document. So if I have a bunch of data and I'd like to sign that, I take my private key, I sign that data, and I create a signature. And then any of you with that document, the signature and the public key, can verify that, OK, yes, Eric actually signed that. In Go, here's how you do that. You use the package ECDSA, because we're cool and we don't like RSA. And we go ahead and we create a private key. The next thing we need to do is actually go ahead and sign a message. Now, it turns out that private keys are bad at signing really long messages. So what we generally do is we take a hash of that message. So we have our message, we take a hash, and then we go ahead and use ECDSA sign with our private key. So we've gone ahead, take the private key, sign the hash, get a signature, and now anyone with the public part can go ahead and verify that hash. In HTTPS, we have these things called certificates. It turns out that certificates are basically just signed documents with some information in them. So in this case, a certificate might have stuff like, this can be used to serve traffic. This can be used for a specific DNS name, like example.com or google.com or facebook.com. And also, interestingly, it has a public key in it. Now, this isn't the public key that signed the document. It's actually a way for you to use the document. So I can distribute this freely, but only the person with the private key can go ahead and serve traffic for example.com. And of course, in order to talk about any certificates and trust, first we have to go over certificate authorities. So there are a lot of servers on the internet, and you're not going to keep a list of every single certificate on your laptop. That'd just be far too many. So what we end up doing is we end up deferring trust into these other entities called certificate authorities. These happen to just be fancy certificates with different fields other than usage serving. And when we go ahead and we talk to a server and it presents us a certificate, if we have a certificate authority that has signed that serving certificate, then transitively we can trust the serving certificate. So rather than trust every serving certificate individually on the web, we end up trusting only the certificate authorities. So now we're going to go into the Go examples, and this is going to be a bit much. This is how you generate a certificate authority. There's a lot on this slide, so I've tried to highlight the important parts. So the first thing we do is need to create a private key for the certificate authority. So we go ahead and say ECDSA generate key. The next thing we need to do is create a certificate template, and that's what this X509 certificate is. Now, there are a lot of fields, but the two important ones are the ones that I highlighted, basic constraints valid and is CA. Basic constraint valid is just a certificate extension, and one of the fields in that extension is a certificate authority. You flip this bit, and yeah, you've created a certificate that can sign other certificates. Now, the really interesting point is we only have one key in the system, so what do we do to actually sign this certificate? And it turns out we just sign it with the same certificate that's the private key for the same public key that's actually in the certificate for a self-signed certificate. You've all heard of these, hopefully. Then we do some marshalling and stuff, and then we use PEM encode and blah, blah, blah. And eventually, we get this. And you all are hopefully kind of familiar with this. If you ever set up Nginx or Apache or whatever, you've seen these blobs. So these are PEM encoded certificates and a private key. It's basically just base 64 encoding of some particular structs that we covered in the last slide. So cool, we now have a certificate authority. The next thing we need to do is go ahead and create a serving certificate. So in our diagram, we have the certificate authority, and now the next step is to generate this blue one on the bottom for the server that allows the server to serve traffic and allows a client to talk to it in an authenticated and encrypted mechanism. This example is also really big, but it's really similar to the certificate authority example. So the first thing we do is we generate a private key for the server because it needs its own private key, and then we create a certificate. And instead of saying is CA true, we're going to go ahead and give it some DNS names to serve behind. This could be example.com, again, google.com, or something of the like, and as well as this extended key usages. The extended key usages, for this case, we need to serve it. This needs to be a serving cert, so we provide extended key usage server auth. Straightforward. The interesting part is when we go ahead and call X509 create certificate, what's going to sign this? Well, we want the certificate authority to sign it, so we need the certificate authority's private key to sign the serving certificate to generate this. So even though the server certificate's public key is in the certificate, the private key for the CA is what we need to sign it. And then we do the same marshalling, and we get about the same thing. And now, if we want to go ahead and serve traffic with those certificates, we load it using TLS X509 key pair, which takes the cert and the private key. And then we just go ahead and create our HTTP server like we always do. But this time, we fill in one field, which is TLS config. And this TLS config takes one argument, which is the serving cert. So we just generate this, we did all this work, and we basically just pass it to our HTTP server, call listen and serve TLS, and yay, we're now serving traffic over HTTPS. On the client side, we go ahead and need to trust the certificate authority, right? Because we're not going to trust the serving certificate directly, we're going to trust the certificate authority. You do this by creating a cert pool, adding the certificate authority, and giving it its own TLS client config. And in this case, you provide the root CAs for cert pool. And then once you call it client get, the client will go ahead, authenticate the server, ensure that it has the authority to serve this particular traffic, and then encrypt the entire connection so that nobody can eavesdrop or tamper. So that's all cool, but what about when a server wants to authenticate a client? So this isn't very common on the open web because you want anyone to be able to go visit your website. But if you have a backend database or a backend service, I might not want anyone to go be able to hit my database or my backend service. So in the same way that servers can present certificates, it actually turns out that clients can too. And this allows a server to distinguish and say, oh, I only want authorized traffic to come into my API. The client certificate has the same trust model as the serving certificate in that the server will trust the CA will sign a client certificate, and because the server trusts the CA, it trusts the signature, then it will trust the client certificate transitively. You're going to get really used to all these examples, but here's the one for the client. So we go ahead and we create a private key for the client, and then instead of server auth, we provide extended key usage client auth. And it doesn't need any DNS names or anything because it's not serving traffic, it's just operating as a client. Then again, the CA needs to sign the certificate, so we call create certificate with the CA private key. We do some marshalling, and finally, we can go ahead and use this as a client to load, to authenticate against the server. That looks eerily familiar as well. So we go ahead and call TLS X509 key pair, and we provide the same certificates field that the server had to the client as well. So we can just provide this, and Go knows automatically, OK, yeah, this is a client certificate. I'm going to present this to my other side. For the server, it needs to trust the CA, same as the client. So we're going to go ahead and provide the cert pool. And then there's this funny little field called client auth. Client auth, by default, doesn't check for any certificate. Totally reasonable default. But there are a lot of weird values you can actually set this to. Like you can require a certificate but not validate it, which is just a bizarre thought. So this is the only field, this is the only value you should ever set this to, require and verify client cert. And if you don't, you better have a damn good reason why not. So yeah, then we serve TLS, we call client.get, and both the client and server have authenticated each other. It's a mutually authenticated connection, and everything's good. So we're done. So this is the punchline, is that it's actually pretty easy to set all this stuff up. The cryptography is terribly hard, but Go provides you the good interfaces to actually do this. But it turns out in real systems, managing all these certificates and private keys is the really, really, really hard part, and is actually the important part to understand and get right. So what's a good example? In our previous coding examples, we've basically assumed that we've had access to all the private keys. Yay, that's fun. But in reality, a certificate authority is never, ever, ever going to give you its private key. And it basically shouldn't. And in the same way, a server should actually never give a certificate authority its private key. That's its private key. So as a good example, certificate signing requests are a way for a particular server to go ahead and call out to a certificate authority and say, hey, I have a key. Would you give me a certificate? If the certificate authority approves of this, it can sign a certificate for the server and send it back. And the nice part about this is that no private information has been shared across this communication. It's just public information. This is actually really easy in Go. So first thing I'll do is generate a private key for the server. And instead of creating a certificate, I just create a certificate request and use create certificate request instead of create certificate. In this case, the server is actually the thing signing this, so we're going to go ahead and pass it the server private key. And then we'll send the CSR off to the CA somehow, probably with like an HTTP post or something. On the certificate authority side, we go ahead and parse that. We check the signature, basically ensuring that the key that signed it is the same key that's in the certificate signing request. And then there's this little comment here about you should probably check to make sure everything's like good and appropriate. We'll get to that later. But let's say that it is, and everything's on the up and up. We'll go ahead, the certificate authority can go ahead and make a X509 certificate and basically just take the fields from the certificate signing request and insert them into the certificate. There's also some fields that aren't available in a certificate signing request, and it has to make intelligent decisions about how to fill this in. And then finally, since we're on the certificate authority, we have access to the certificate authority's private key. We go ahead and use that to sign the certificate and send it back to the server. What about authenticating a CSR? So I'm going to give a hypothetical about, I have two services and they're running in GCP. I promise this works with other cloud providers, but this was just easier if we only did one example. So I have two instances. One is running foo.com and one is running bar.com. And they're both going to need certificates, so they send certificate signing requests to my certificate authority. And the certificate authority now has this problem, because it's like, well, I got a couple of certificate signing requests, but I have no idea which is appropriate. Like, is this actually foo.com, or is this bar.com trying to be tricky? So in GCP, at least, there are metadata APIs available to every instance. And ultimately, what we want to do is we want to basically determine that a particular certificate signing request is coming from a particular instance. So if I'm on foo.com or bar.com on those instances, I can hit these APIs, instance service account default identity. That'll spit out this. Who knows what this is? It's a JWT. This is not a JWT doc, so we're not going to go into all of the glorious, fun details of the awesomeness of JWTs. But essentially what this is it's a signed document by GCP itself. So this is actually the platform attesting to this request came from a specific instance that is running in GCP. And this document will be different depending on what instance you requested from. When you go ahead and unpack that and verify its signature, you'll get stuff like the instance ID and project name and all the good stuff. So when we go back to this other example where we're sending CSRs, you might consider something like, OK, these instances need certificates, but they're also going to include that JWT. And that way, the certificate authority can actually look at this and have an attestation from the platform that you're running on. This might be similar on AWS. There's a metadata document that's signed by AWS. In Kubernetes, there's stuff like container identity, which you can use to bootstrap this. So on the certificate authority side, we go ahead and parse the CSR. We check some signatures. And then we pull that JWT. We parse it and get the instance ID. And now we can start to make intelligent decisions about when we're going to approve CSRs and when we're not. And I think that this is a really fundamental point of the way that you might distribute certificates. Don't just generate them locally and SCP them to boxes. Actually bootstrap them off of some other authentication mechanism. And that is undoubtedly going to be the provider or the platform that you're running on. Let's talk about everyone's favorite topic. So a really simple way to revoke a certificate is something called a revocation list. Basically what this is it's a list from a certificate authority that says, these certificates are revoked, don't trust them. When a client goes ahead and talks to a server, it can now check that list and say, oh, is that server's certificate in this list? And if it is, then things fail and blah, blah, blah. In Go, the way you do this, or the way a certificate authority would do this, is that it would go ahead and create a certificate, a list of revoked certificates, just including the serial number. Serial numbers are supposed to be unique, so hopefully this works. And then it'll go ahead and say, use its the certificate authority's private key to create a CRL. And that is just a bunch of bytes, and you can go ahead and distribute that to all your clients. On the client side, you do need to add specific logic, because Go doesn't do this by default. But you can use this thing called verify pure certificate as part of the TLS config. This allows you to do additional verification on the certificates you receive from your peer, from the other side of the connection. So we'll go ahead and parse this. We'll check that the CA actually signed it. And then we'll just loop through all the certificates that were presented by the other side and say, are they in this list? And if they are, we bail out and say, sorry, the certificate was revoked, and everything's good. Revocation lists have issues, I think is the best way to summarize this. One of the most damning things about a revocation list is that you can theoretically put like a revocation list endpoint in your certificate, so clients should check that. But basically, every client fails open, meaning if they can't reach that endpoint, they'll be like, oh, whatever, I'll just trust the certificate anyway. This is a huge argument on the internet, and I'm not going to get into it. But I think a TLDR that's helpful is that certificate revocation lists are generally good for a smaller set of certificates. So if you're running infrastructure and you can sort of count in the hundreds or thousands the number of certificates that you're using, certificate revocation lists are totally reasonable. If you're talking about the open internet, they might have some scaling problems. To address this, there is another form of revocation called OCSP, the Online Certificates Status Protocol, or something like that. Basically, it's a way for you to go and ask a certificate authority and say, hey, is this certificate still valid? This specific one. And the certificate authority is then required to send you a response, whether or not it's valid, to say, yes, I got your response or request. Here is a signed, basically, document saying that this certificate is valid for the next day or next week or something like that, something that's generally much shorter than the validity of the actual certificate. This has a few problems with this particular design. One is that your servers might be prepared to handle a lot of traffic, but your certificate authority might not. Another sort of more insidious one is a privacy concern. So if I have to go and check with the certificate authority every time I access a website, the certificate authority now knows every website I've visited, which is not good. To deal with this, there's this thing called OCSP stapling. And the way that this works is that it still passes the same signed object from the certificate authority, validating a particular certificate. But instead of you making the request, the server makes it the request on your behalf and every other client's behalf. So it's one request per amount of validity that the server makes. And then when you go ahead and talk to the server, you're actually going to receive the OCSP result as part of the TLS handshake. So it's just a TLS extension that is used by the server. In Go, the way you do this is you use the TLS certificate. This is slightly different than the X509 certificate, but it just has this field called OCSP staple. If you fill that in, then the Go handshake will include that extension and present the OCSP staple to the other side. The way you do this for a certificate authority is that you use the crypto OCSP package to create a response and sign it with your certificate private key. And then you can include that staple as part of your certificate, and magic things will happen, and your other side will get it. Then, for the client, you go ahead and verify the OCSP. This is a big block, but basically all it does is it pulls the OCSP response out of the connection state, goes ahead and parses it for the certificate that you've requested, checks the signature, and says, OK, this is all good, and continues. And then finally, when you want to use this, you use dial TLS instead of TLS config. Dial TLS exists as an alternative to this. You won't even, if you use this on the transport, you won't actually use the TLS config at all. But you can now pass your custom TLS config and then do an additional validation as part of this request, validating OCSP responses that you get from the server. And if the server doesn't have it, you might just want to bail out. So what happens when you want to rotate a CA? So the way that you rotate client certs and server certs are kind of easy, right? You just get another one. But CAs are kind of hard because they stick around and people trust them and that kind of thing. This is actually the simplest example or slide that we have. So it turns out when you do something like load a certificate authority bundle, that certificate authority bundle can just have as many certificate authorities as you want in it. So if I'm a certificate authority and I generate a new certificate authority, or generate a new certificate that I use for this, I can just include my old and new one in this bundle, and clients will transparently just pick this up. Then after a lot of rebooting and a lot of waiting for old certificates to roll out of the system, eventually I can then pair that certificate authority bundle down to just the new CA, and voila, I've gone and rotated my CA. A really popular setup for hosting environments is to host multiple websites behind the same endpoint. And a lot of the cloud providers will actually terminate TLS for you. How convenient. But this presents a problem. Because if I'm a client and I go and hit a proxy that's going to terminate TLS and wants to do the TLS handshake, and I'm hosting foo.com and bar.com, how do I know which certificate to present to the client, right? Do I present the certificate for bar.com or foo? And the answer is this thing called server name identification. It's this very convenient function or extension in TLS that allows you to include the server name you're requesting in the TLS handshake. So you say, hey, I would like to talk to bar.com. And then your server knows and says, OK, yeah, you need to talk to bar.com, and I have the certificate. In Go, if you just provide multiple certificates, everything will figure itself out. So this example is actually overkill, but it also demonstrates that you can be extremely dynamic with the way that you get a certificate for a particular connection. So in this case, you could load a couple certificates, and then you can use the get certificate method to actually inspect the client hello for the TLS handshake and say, OK, based on the server name, I'm going to give a different certificate. You could also dynamically look stuff up in a database or something like that. Lots of ingress controllers in Kubernetes do this because they get requests and need to look up secrets, as an example. Server name identification has been an interesting wild ride. So server name identification is in plain text, which means that anyone inspecting your connection can see this. The government of Kazakhstan right now is using this to prevent you from accessing certain websites and strongly encouraging you to install your own government-sponsored CA, as an example. There's been a lot of efforts to basically fix this with stuff like encrypted SNI. Cloudflare is one of the companies that's doing this. But in Go, there's no support. This is because encrypted SNI is an arbitrary extension to the TLS handshake, and Go doesn't support them. You need to get this into the standard library in some sort of API-driven way. There's also some interesting results of stuff like domain fronting. Let's Encrypt had some weird SNI challenge issues. I would strongly recommend that you go look all these up because they're interesting and sort of demonstrate that SNI has been a really sort of well thought proposal, but has had a lot of fallout. So what about clients? So in the same way that I might want a client to differentiate between different servers on the internet, a server might get multiple requests from different clients and need to say, okay, I understand that you all have certificates, but I actually want to treat you differently based off of having different levels of access or something like that. A good example is, let's say that we want to allow the green key here to access the database, but the orange one, that'll be read-only, you won't have write access. For this, you basically just use a field in the certificate. There isn't really a standard for this kind of stuff, but the common name is a perfectly reasonable field to pull out of a certificate. So at the application level, you can go ahead and take an HTTP request, look at the certificates that are presented and were verified, pull out the leaf, and return the common name, and then use this as part of your application to say, okay, we're going to do different things based off of which certificate was provided, and actually do authorization. Hardware-bound keys are a lot of fun. I work with these a lot. So on the left here is a TPM, a Trusted Platform Module. This is basically in all sort of hardware qualified by Windows. They must have this. And things like Chrome OS and Mac also have similar concepts. But basically, it's hardware in your computer that can be used to store private keys. And you actually don't need anything, something like burned into the, the hardware. You can actually use stuff like security keys to do this. I think we all kind of intuitively know this with our U2F challenges, but you can also just store certificates in there as well. The way that hardware-bound keys work is that the private key is not in memory, it's in the hardware, and never shall it escape. So from user land, you can't actually interact with this in any way, but the way that you then get the private key to do things is you use APIs. So an example of an API might be a signing request. So I might pass it some data and say, hey, don't give me the private key, but have the private key on this particular hardware device sign it. Now, when I was explaining private keys to my friend, he was basically like, well, I can still access the private key, right? What's the security benefit here? And that's absolutely true. But it is really nice if you get hacked that the attacker has to persist. It is a lot worse if an attacker gets in, makes off with your private key, and then you have to explain to the auditors and say, oh yeah, I don't know where that is, and I don't know how long it was accessed for or what they were doing with it. So while hardware-bound keys are not a perfect solution, they are certainly a really good hardening solution and sort of expected in certain environments. The way that you give a hardware-bound key or some other sort of key implementation to Go is you use the private key field in a certificate. Now there's a little bit of a comment there that a private key is just an empty interface. It says nothing. But a private key can also implement conditional interfaces based off of what you give it. So in this case, if you give it an ECDSA key, if it implements this method crypto signer, which is the method for signing, then the TLS library will just go ahead and use this as if it were an in-memory key. YubiKeys actually have a really cool feature called PIV. Again, you can do stuff like GPT with YubiKeys, but it's always just a mess. So PIV is just a standard protocol. I think it's used in government agencies and stuff like that. But it's basically just a way of assigning certificates to people. And you can use this particular package, the YKPIV package, to go ahead and authenticate against your YubiKey. And then you can generate an elliptic curve key on your YubiKey instead of in memory. And it returns this slot object, which can be then used to sign things. So in this case, we might create a certificate signing request. Later on, when we get the certificate response from the CA, we update the slot with the certificate, so it's now a full-fledged certificate and key pair. And then we can just go ahead and use the slot as part of our TLS certificate. And when we present this to a server, it'll just use this automatically and be calling out to the key on the YubiKey rather than the key in memory. And the TLDR here is basically never assume that your keys are ever in memory. Never assume that never take an argument that's like RSA private key. Always assume that a key could potentially be in memory or potentially be in other key management systems, and just pass around crypto private key in all of your APIs. Let's Encrypt. Let's Encrypt is amazing. It has been a huge reason why the internet is moving more and more to HTTPS, and Go has amazing integrations with Let's Encrypt. Let's Encrypt is a certificate authority, and the basic way it works is that when a server goes ahead and sends a certificate signing request to Let's Encrypt won't sign it immediately, but will start to issue challenges. So it'll say, hey, prove that you control this domain. This might be something like, I want you to host this really long string at this particular HTTP address. Or I'm going to go reach out and do a connection, and the TLS handshake has to have this next proto in order for me to prove that you have control of this domain. So if you go ahead and say, here's the proof, Let's Encrypt will sign you a certificate automated for free that is trusted by browsers. So use this, please, please, please. Go has a really awesome package called AutoCert. This example is actually longer than the example that you can use AutoCert for. If you want to get into the details, though, you can basically use stuff like AutoCert Manager and pass it a specific cache directory. You then go ahead and use a TLS config during your HTTP server, and this will actually just work. You'll now have a certificate for this server, and you'll be serving traffic with a trusted certificate. The AutoCert dir cache is an interface that allows you to coordinate state across many different servers. So normally, this would just write a bunch of key material and other stuff to a directory, so keep that directory safe or whatever. But you might be able to also store this data in an encrypted bucket or something like that, and share this between many different servers that would all then be using the same cert, and this would work out really well. Certificate transparency is something that's actually, it sounds relatively new, but it's actually been shipped and is sort of an integral part of Chrome today. So the problem that certificate transparency tries to solve is I'm an evil CA, and I go and issue a bad certificate. And the question now is, how would any of us know? So if I'm a very small certificate authority and I want to go ahead and issue a certificate for Google.com or Facebook.com, that would be a really bad scenario, particularly if we didn't have any insight into that. So there have been other sort of tactics like certificate pinning to try to mitigate this kind of risk. But in reality, the fundamental problem is that whenever you sign, if you're a public CA and you sign a certificate, that is actually a public statement that anyone's browser will now trust. And the reality is that this shouldn't ever be secret. If you ever sign a certificate, this should now be available to anyone in the public to audit. The certificate transparency log is a log of every certificate. So anytime a certificate authority ever issues a certificate, it must be in the certificate transparency log. This is a cryptographic log, so you can actually prove things like you can prove that it hasn't been tampered with, that a certificate hasn't been removed, and this allows many people to host certificate transparency logs, and for us to all sort of pick and choose. The way that we enforce this is that certain clients like Chrome, when they go ahead and reach out to a server, included in the certificate response is going to be sort of in the same way that OCSP is the signed certificate timestamp. Now, you can go ahead and take that the signed certificate timestamp and use that to look up in the certificate transparency log and identify a particular certificate. So this means if you get a certificate and it's not in the certificate transparency log, you can now not only not trust it, but start raising a lot of alarm bells for the person who's supposed to control their certificate. The certificate transparency library in Go is the certificate transparency Go library. And you can use this just to hit like Google's certificate transparency endpoint. Now, you can do things like validate the handshake response, but you can also just dump certificates. So a good example is that we create a new client. We'll go ahead and take the head of the certificate transparency log, and then we'll just start iterating through entries one at a time. So this one will dump the first 5 logs, and you'll get something like that. Now, the way that all of you can use this is if you're running a website you might want to occasionally look at the certificate transparency log and say, oh, a certificate was just issued for my servers or a domain name that I control. Do I actually know where that certificate is? Is it in my inventory? Or is this someone else because they got access to a DNS record or because they got access to a private key? And that's basically all I have right now. PKI is it's a big topic. And it is sort of ephemeral, like there's no clear definition of what PKI is. But I'd like to sort of leave you with some closing thoughts. Just use HTTPS. Even if you're writing backend services, stop using HTTP to allow your clients to hit this. This is very people are gonna get mad at me, but really, you should be doing this work anyway. Because in production, it's going to need HTTPS. So it's a lot easier for you to do stuff like set up some scripts for the getting started thing that generate certificates so your clients can use them. But generally, unless you have an extremely good reason to use HTTP, just use HTTPS. Use stuff like this to generate your certificates and manage them within an organization. And be safe out there, y'all. Thanks.